Welcome to Engineering 1166. This is the lecture for electrical and computer engineering dedicated to control systems. Control systems are commonly seen in our daily life. And we use control system because some system by itself cannot operate to meet certain desired performance. And this is commonly seen in our daily life. And the goal of a control system is to make sure the system at hand can operate according to a user-defined behavior. And what is more importantly, we want it to be able to accomplish this in an automatic manner. And what are the desired features of control systems? First of all, we want it to be stable. We don't want it to fall apart easily. We want it to have a certain self-diagnosis and self-recovery capability that we can return to a desired performance even though there can be some uncertainties, unexpected events, and so on. Secondly, we wanted to have the capability of reference tracking, meaning when you set a certain desired performance, you want it to track and behave exactly as you have expected to do. And third, when in terms of uncertainties, unexpected environments, unusual environments, or you have certain disturbances or noise, you want the system to be able to reject them and to compensate it properly such that you can still have the desired performance. And we can think of a control system in our daily life like air conditioning, where you set a temperature on a thermostat, and the air conditioner will run when it requires to do or heat up this room when it requires. And its disturbance could be, people go in and out of the room, can open the doors, let the colder or hotter air in. Someone may open the window, right? Maybe someone is boiling coffee in the room that can make this a little bit hotter than usual. You can think of a cruise control system on your car where you set the desired speed to be 78 miles per hour. You want the car to be driving exactly at this particular speed. No, not slower, not faster. Despite of the road conditions, the wind condition, the weather conditions, and so on. The basic approaches of control are usually categorized into two types. One is what we call the open loop control. So when we have a control system, we usually have a plant. This is the physical system being controlled, right? It could be the room when you talk about air conditioning. It could be your car when you talk about cruise control. And you care about the actual output. It could be the room temperature, could be the speed you're driving. And to make that happen, in open loop control, we have to have a desired output. This is the desired performance, desired behavior. We usually call it the reference. And you want your output to behave, to copy your reference. And to accomplish that, you need to have a controller, which is a device that calculates the control signal based on the desired output and the feature of your plant. And this can be accomplished and realized by a computer, circuit, or by pulley, by chains and belts, mechanical system, or with springs and dampers and so on. The actuator in the middle is the device that will do the work, the actual work. And it will transform the control signal calculated by the controller to an actual action to be injected to the plant. It could be motors, could be drive, could be valve, could be pumps, and so on and so forth. Could be water faucet. But we're living usually in a non-perfect world. We have to think about possible disturbances and unexpected occurrences of certain events. Now, closed loop system starts with just what we have in an open loop system: controller, actuator, and plant, the same as before. But to close the loop, we're continuously monitoring the output, the actual output of the plant by a sensor, or sometimes called a transducer, and compare the sensed or measured output with the desired output, the reference. Okay? As you can see, we have the plus and minus sign here. And the difference of the desired and actual outputs is what we call the error signal. And now the error signal will become the one that will drive the calculation, the computation, the controller, and then the control signal will be sent to the actuator and then to the plant. Now, the reason we call it closed loop is because now you have a closed loop. The loop refers to from the desired output, the reference, to the actual output and coming back. And because we're feeding back the output to compare with the desired reference, this is also called a feedback system or feedback control. Now, in addition to the disturbances that you have to care about as you have in the open loop system, you also have to worry about the noise and precision in the sensor. And this can become very critical in designing a closed loop system. So a typical example like the air conditioning system we talked about earlier and the air cruise control system are examples of closed loop feedback control. Now, open loop control, the pros and cons are as follows. First of all, open loop control does not measure or monitor system output. It uses some predefined calculations to come up with the control signal. So there's no on-the-fly input adjustment. If certain unexpected things happens or certain disturbance, the control system won't take notice. Will still use the predefined control signal to drive the plant anyways. Then of course this may not be a desirable feature. And the control system performance may be easily affected by the disturbances in the plant or outside the plant. But the pros is open loop control systems usually very cheap to implement. Okay? You don't need a sensor, and the control actions the calculation by the controller is usually also very simple. And examples are easy. Talk about room temperature, right? Most of the rooms nowadays have air conditioning, but there are some rooms that do not. For instance, some of the classroom buildings at UConn does not have air conditioning. And what happens in a hot day is you will find the electrical fan in the room. But the fan itself does not monitor room temperature. You can only set the speed of the fan to low, medium, and high, right? And no matter how hot or how cold the room is, the fan itself cannot adjust the speed. This is clearly open loop. If you want to close the loop, then you want to have an human operator go there, adjust the speed based on the feeling. But now you're doing the sensing, the human body becomes the sensor. And you yourself will be doing the controller to change the fan speed. Closed loop or feedback system continues to monitor the output and utilize the information to adjust the system input accordingly. And it has the capability to reject internal output and external disturbances if you design the system properly. But remember, because you have the sensor and the controller in the feedback system is usually more complicated, the system overall performance heavily depends on the quality of the sensors and controls you selected. And because of you have sensors and those complex controllers, it can be relatively more expensive compared to open loop control. And examples we have already talked about, right? We have air conditioning, we have cruise control. You can think about other examples. For instance, your phone, right, can adjust the backlighting strength depending on the lighting conditions in the room or in the environment. If it's too bright, you probably want to have brighter screen. If you're in a really dark room, the screen light will be adjusted automatically to a relatively low level. That is feedback control as well. Quick theory of control. The control theory study starts usually, we view this as the start of the control theory study. The first industrial revolution, late 1700s, early 1800s. And James Watt is usually viewed as one of the pioneers of control applications. And one of his contributions is to apply what is called a fly ball governor to regulate the speed of steam engines. Okay? And this is a sketch of this design, and this is the two pictures at the museum that showcase James Watt's design of the steam engine. And this is the steam ball regulator here, here, and here. What happens is you see the chain connects this rotary governor with the steam engine, and when they rotate, this guy will rotate with the same speed. But if this rotation becomes too fast, okay, this two ball will fly up. This is what we call the centrifugal force, as you can have learned in physics. And when this two balls go upward and outward, will push up this particular device. And if you connect this lever with, let's say, the valve to the steam engine, when you push up, we'll close the valve, we'll let less steam into the engine. That will help reduce the speed. Okay? And from this sensing of the speed and calculating by designing, the force, the weight of the steam ball, and also the maybe you want to apply a spring to apply certain force. This becomes a controller, and the actuator will be the lever and the valve that connects this particular device with the steam engine. And you have all components you need. And from then on, James Maxwell, yes, the Maxwell that's known for the Maxwell equations in physics in electromagnetic fields, analyzed the stability of flyball combiner-based steam engine feedback control. And from then on, the entire world starts studying this control theory in Russia, in Europe, and later in America. And with more applications in the war and later in the aerospace applications, nowadays we're looking at a huge amount of very valuable results that are commonly applied in modern devices, equipment, and also being used in our daily lives. Now here are some illustrations that showcase some of the basic university lab-based control application. This is what we call the inverted pendulum. A pendulum is usually pointing downward, but of course, if we make it more general, we can make it go upward. It's like you want to stand a pencil on the table. And of course, we know it's very tricky, very difficult, and a small disturbance or shaking the table, the floor, can break the balance and make the pencil go on the floor. But if you can continuously monitor the speed or the angle or the position or the pose of the stick or the pendulum, it's possible to stabilize it. As we can see in this video, I will apply certain disturbance here, and the card will respond by measuring how much offset from the upper position the stick has, and move around to make sure the stick still point upward, won't fall to the ground. And the inverted pendulum can be viewed as a simple example of, for instance, rockets, right, where the thrusters is at the bottom to maintain the pulse direction and the speed of the rocket. You can think of it as a human standing on a Segway or a hoverboard, okay, which you also have this particular application. And of course, you have to design this hoverboard or Segway properly such that the human user do not fall to the ground easily. The second illustration is what we call the maglev, magnetic levitation. This is a simple version or a simple application that can be generalized to, for instance, high-speed train systems or some of the high-rise building elevator systems that use magnetic force to levitate a certain object. And this is also an unstable system because the gravity and the magnetic force have to balance. And if you apply certain disturbance to this, will break the balance easily. And the control system has to calculate the voltage or current to be applied to this electrical magnet and apply the force to balance the gravity even in the presence of certain disturbance. Right. The third example is a robot, which shows how a robot can track a determined path using a webcam being the vision sensor, such that this will tell the robot which direction to go, and then the actuator will be the motors and the turning motors underneath the robot that tells or dictates the direction and speed where it goes. You have to rotate here and there to survey the area to find this particular path that this robot is designed to follow. And think about an open loop version of this is you design the path, you put this map to the robot and let it to follow this particular angle in a perfect plan. But if someone happens to maybe run into this robot, change the course or change the position a little bit, and for instance, if this guy is not traveling on a very level surface, your perfect predefined travel plan may not work, and this robot can easily go off course and will not be able to follow this path properly. And this path following application may happen, for instance, in manufacturing facilities where you have automated guided vehicles that transport parts, drops from one place to another. Can be, for instance, in an Amazon warehouse where all the shelves, all the products are stored on big pallets that will be transported by those robots that from one place to another, such that the operators will be able to pick and place and put the desired product that the customers ordered on the truck or delivery transportations. So this is the iRobot application. This is the end of this lecture. Through this lecture, you should have learned the basic concepts of control systems, the basic approaches of control, and should be able to identify the components of an open loop system, a closed loop system, and give some examples from your daily experience, personal experience, the examples of open loop control systems and closed loop control systems, and can identify the components from those examples.